Welcome to Stochastic Simulation Lesson 1. We're going to talk about Python, the programming language, and the uniform distribution in probability. I am Ronald Johns. Our goals are the following. We will use Python, the programming language, to generate a sequence of random numbers coming from a uniform distribution on 0, 1. We will also look at histograms to see how close it comes to uniform. We'll use Python to simulate the rolling of one fair die 10 times, noting the upper face on each roll of the die. We'll print out the results of each roll. Also, we'll use Python to simulate the rolling of two fair dice 1,000 times and then again 10,000 times, and plot histograms in each case of the distribution of the resulting sums of the two dice. This will give us some idea of how the uniform distribution works. So let's talk about generating a sequence of random numbers that come from a uniform 0, 1 distribution. First of all, computers, classical computers, the ones like our desktops, can't generate numbers that are truly random. What we'll do instead is use the computer to generate what are called pseudo-random numbers. Pseudo basically means false. They're going to look random, but they're not really. They appear to be random, and they will pass various tests of randomness. There are books on random number generation and how to test them to see if the generation method is good enough. The sequences that we come up with are deterministic. They're not random. And for instance, if you have the computer code that generates that sequence of numbers, you could use that code to predict each number generated in the sequence. But most likely we don't have the code in front of us. All we have is a function that spits out what look like random numbers, and we don't know how they were generated, but they really look random and have certain probability distributions, a specified probability distribution. So let's discuss random variables. Intuitively, we can think of a random variable in this way. We perform an experiment, maybe over and over again. For each time we perform this experiment, there's an outcome. The value of the random variable depends on the outcome. Here's one example. Flip a fair coin 5 times. And let x be the number of heads minus the number of tails. In that case, x for the outcome heads, tails, heads, heads, tails would be 3, number of heads, minus 2, the number of tails, and so x would equal 1. This type of random variable is called a discrete random variable. And here's another example. Let's randomly choose a number between 0 and 1. We're choosing a real number. It might even be irrational, who knows. Let x be that chosen number. In that case, x is going to be what we call a continuous random variable. So let's first talk about continuous random variables. As we go along in this series of videos, we're going to be interested in both continuous random variables and also discrete random variables. The first type that we'll talk about will be continuous. I guess this is kind of opposite of what many people do when talking about random variables. Continuous random variables will have a probability density function, which we call a PDF, and also a cumulative distribution function, which we'll call a CDF. That can be used, both of these can be used to calculate probabilities involving that random variable. So let's talk first of all about the probability density function of a continuous random variable. So let's suppose that we have a random variable x, which is going to be a continuous random variable, and what we have is some function of x. F sub capital X will be the density function for this random variable capital X, and I want to tell you something about the value of this function at a point. it's going to have the following property. The probability that our random variable is between two numbers, real numbers, a and b. The probability that x is greater than a and less than b will be the area under the curve from a to b, the area under the PDF. So in this illustration here, this curve that we see that looks something like this is going to be the probability density function. And if you have 2 points A and B, as we have here in this diagram, this probability is just going to be the area under this curve from A to B, this shaded area right here. The area under the curve starting at 0, which actually is right here on this graph, and going up to that curve. Okay, if you had calculus, you know that this area is going to be the integral from a to b, that density function f of capital X evaluated at x integrated with respect to little x. Probabilities are always between 0 and 1. So the total area under this curve, the area from, in this case, maybe 0 out to infinity, which is way out here, would be 1. And so this tells us how to use a PDF if we are given its formula and if we can integrate it. Sometimes this integral could be very hard to evaluate, and it used to be that we would have to use tables to calculate probabilities like this. There were thick books that just had table after table after table full of zillions of numbers, and you would look up these probabilities. These days, calculators and computers can often numerically calculate these probabilities for us. Still talking about continuous random variables, there's another function called the cumulative distribution function. And I'm going to call that cumulative distribution function capital F sub capital X. And we can evaluate this function at a real number x. And often the cumulative distribution function looks something like this. It starts way out here at 0, and as you go to the right, increasing values of x, it gets closer and closer to the value 1 as we go. 1 here is shown here. And so we can see that curve is getting very close to that horizontal line. Let's say y equals 1 if y represents numbers on this axis over here. So if we look at capital F sub x at some number b, that's going to be defined to be the probability that x is greater than minus infinity and less than or equal to b. And if you know calculus, this will be the integral from minus infinity to b of the density function, little f of x, evaluated at a number x dx. Now, given that we have this definition, if you want to calculate the probability that our random variable x is greater than a and less than or equal to b, we can calculate that by looking at the cumulative distribution function evaluated at b minus its cumulative distribution function evaluated at a. Let's talk about the uniform 0-1 distribution. Uniform distribution on the interval from 0 to 1. The probability density function is the following. F of x equals 1 if x is between 0 and 1, and it's 0 otherwise. So this is a fairly simple function to look at. So here is the graph of that density function. Between 0 and 1, the function has value 1. So it's constantly 1 here, horizontal line. Everywhere else, the function has a value of 0, over here and also over here. Suppose we want to use this density function to calculate the probability that our uniformly distributed random variable x, uniform 1, 0, 1, the probability that x is between 1/2 and 3/4. In that case, it's going to be the area under this curve from x equals 1/2, which is right here, to x equals 3/4, which is right here. So it's equal to this area, and this is a rectangle, isn't it? It has base of 1/4, and the height is 1. And so what that tells us is that this area is going to be 1/4. So the uniform 0-1 distribution is a continuous probability distribution, and its PDF, remember, is 1 if x is between 0 and 1, and out here past 1 and over here past 0, the function is just 0. So if you want to find the area, if you want to find the probability that if you randomly pick a value x from this distribution, that value x is between two numbers a and b, we're assuming that a and b are between 0 and 1, it'll be the area of this rectangle. The height of this rectangle is 1, the base is b minus a, and 1 times b minus a is the area, which is just b minus a. We're going to talk about the function called random. It's a Python function that generates real numbers, not integers, that appear to be random and appear to come from a uniform 0-1 probability distribution. Each time you use this function, it'll give you a number, and if you look at the collection of numbers that it generates by using this function over and over again, it will appear that each real number in the interval from 0 to 1 is equally likely to be generated. Now, this function is not available right at the beginning when you write your Python program. You have to grab this function from a library. Now, someone had a really good idea. They created a library, a Python library called random, same name as this function. And what we'll have to do is import this function up here from the random library. And in fact, we could just import the entire random library and then call this function from that library. So here's a program to illustrate the use of this function. From the library random, we will import the function random. After that, we can use this function random. So here we have a for loop. For k in the range, and then parameter 10 here, we'll do the following. My rand num equals, and then I'll call that function random. Then I will print the string my rand num equals, and then the value of that my rand num, that variable that was assigned up here. When we execute this, the first time through this loop, when k equals 0, we get my rand num is this number. Second time through this loop, when k equals 1, my rand num equals this. And we continue to generate 10 values of my rand num here. We have these numbers, and if you look at these, they look pretty random, but it's not very evident that they're uniformly distributed between 0 and 1. We'll have to work a little bit harder to show that. So let's talk about histograms, how to make histograms using the Python programming language. There's a graphics library called matplotlib that can be used in Python to generate plots and graphics and so forth. And inside matplotlib is pyplot, a library within matplotlib. Pyplot, and matplotlib for that instance, has functions to display all sorts of graphics such as plots, bar charts, histograms, and other things. To make a histogram, we need to import the pyplot library through the bigger library, matplotlib. So when we make our histogram using functions that are built in for making histograms, we are going to have to specify class intervals, which are also called bins, for the histogram, so that our software can do some computations and show how frequently data values that were stored in a list occur in each of those subintervals, those class intervals. Here's a summary of the situation. It was produced using Gemini artificial intelligence, available from Google. Matplotlib is the entire plotting library for Python, while pyplot is a specific module within Matplotlib that provides a simple state-based interface for creating plots. Pyplot acts as a wrapper around the more comprehensive object-oriented interface of the Matplotlib library. The primary relationship is that pyplot is the main entry point and an integral part of the matplotlib package designed to make plotting easier and faster, particularly for interactive use or simple scripts. So let's look at an example of a histogram and get some sort of idea of how we would use Python to make it. First of all, we're going to have a variable bins, and it contains a list with elements 0, 0.1, 0.3, 0.6, and 1. What this gives us indirectly are the class intervals. When we make our histogram, which looks something like a bar chart down here, we have one interval going from 0 to 0.1 right in here. Then we have another interval, class interval, going from 0.1 to 0.3. And then we have another class interval over here going from 0.3 to 0.6. And then one more class interval, looking up here, going from 0.6 to 1, which is right here. Right here is 0.6, and over here is 1. So we have bars over each of these class intervals. So on the horizontal axis, which you might think of as the x-axis, we have our class intervals that are found from this Python statement. The bins is a list, contains a list, and these are the endpoints of all of those class intervals that we saw down here. So now let's create my num array. My num array is going to equal, and then we have a whole bunch of numbers in here. And let's see how many of those numbers fall between 0.3 and 0.6. Actually, the interval that we're looking at here does not contain this endpoint, 0.3, but it does contain this upper endpoint, 0.6. So if we go through this list and find all of the values in my num array that are within this little range, they're illustrated here in red. 0.508 is between 0.3 and 0.6. So is 0.327, 0.303, 0.306, 0.428, 0.383, and 0.534. If you count these, we have 1, 2, 3, 4, 5, 6, 7 values that are between 0.3 and 0.6. So we draw a bar, a vertical bar over that class interval that has height 7. 7, as you can see, is shown here on the vertical axis. The height of this rectangle is 7. So what happens is the heights of each of these rectangles tells us how many data values are within the class interval. To produce this histogram graphically, we would use a statement like this. I'll introduce a variable called myHistogram, and it's going to equal the following. PLT is going to represent the library pie plot. We'll see this in code later. And then pieplot.hist, and then we give it some parameters here. The first one is this numeric array of data values. What are the bins that we're going to use on the vertical axis? And the edge color is black, says that each of these rectangles has black edges. And after this statement is executed, the histogram is not shown yet. We can show it by using plt.show. And notice the parentheses here. Those are necessary to recognize that show is a function in that pieplot library. So we saw that the class intervals are these, and then we saw that the bar heights answer the questions of how frequently do data values fall in each of these class intervals. And as we showed over here with this example, we were looking at the class interval of data values in that list that are greater than 0.4 and less than or equal to 0.6. And there were 7 data values within this class interval. Let's see what we can find out about this function random by using Gemini Artificial Intelligence. Here's an overview that I got by asking for that sort of information. The Python random.random function returns a random floating point number in the range from 0 to 1. The square bracket here means that it could return the value 0. The round parentheses at this end tells us that the upper bound for values coming from this random function can approach 1.0, but it cannot be 1.0 itself. 0 is in this class interval, 1 is not in the class interval, and all of the values strictly between 0 and 1 are also in this interval. So what we're talking about basically is the range of this function random coming from the Python library random. Here's some characteristics. It's a semi-open interval. This interval here is semi-open. People also say half open or half closed. It includes 0, but it excludes 1. But everything in between 0 and 1 is also in that interval. Mathematical notation, we could say this is a set of all x such that x is greater than or equal to 0 and less than 1. There's some precision discussion here. They say it has 53-bit precision. My guess is that it actually has 64. It uses a 64-bit word, but only 53 bits of that are used in the value of the function, normalized in some way. Some other bits are used to raise 2 to a power or 10 to a power. We'd have to look it up, but it's given by IEEE 754 double precision floats. So that's something we could research. What we have in this random function is a uniform distribution. Every value within this range has an equal probability of being selected. All values strictly between 0 and 1 are just as likely to be chosen as an output as any other value that could be from the output of this function between 0 and 1. So let's investigate this function random just a little bit more. Why do we say that it has a uniform distribution, this random number generator? So let's look at this program and some of its output. So from random, the library random, we're going to import the function also called random. From matplotlib, we're going to import pyplot as plt. Instead of having to write pyplot often, we'll just use this more or less synonym for it, plt. Import numpy as np. So let's see what happens here. We're going to plot a histogram with actually, I guess, 9 subintervals. And so we have plot.figure1. So we're going to create something called figure 1. And we're going to start with an empty list in the variable myUnifNumArray. This is going to be a list of numbers generated by using the random function. So then I'm going to set the bins. np dot is what? This is going to be a function called from numpy, which we can refer to in our program as np. So from numpy, we're going to call the function linspace, and we're going to give it the parameters 0, 1, and 10. What this does is it produces 10 real numbers that are equally distant from each other, at least on a line. It's going to divide the line, maybe I should say, into subintervals. It'll divide 0, 1 into subintervals using 10 points. So that will give us 9 subintervals, because there's one point at 0, there's another point at 10, and a whole bunch between 1 and 10. So then we'll say for k in range 10,000, so we're going to make a loop here that executes 10,000 times. myUnifNum equals random. So we just generate a random number, we store it here. Then the next thing we'll do is put it in myUnifNumArray. So myUnifNumArray dot append myUnifNum. So the UnifNum that was just generated here is appended to myUnifNumArray, which is actually a list. So I guess it's a little bit confusing. Remember that we started with myUnifNumArray equaling empty. So when we go through this list, through this iteration, after we've done 10,000 iterations, myUnifNumArray will have 10,000 numbers in it. And so then we'll plot those numbers. Well, we'll make a diagram, a histogram that is, using that data that was created in this array, this list actually. And so my histogram equals plt, which tells us we're going to call a function from pyplot. The function we're calling from pyplot is called hist, H-I-S-T. And then we'll pass it that array or list of numbers. We'll pass it the bins, and we'll say that the edge color of the rectangles for this histogram will be black. And then plt show will actually show that, display that histogram in a graphics window. If we run this program one time, we get a histogram that looks something like this. If we just run the same program without any changes a second time, in this case we got a histogram that looks like this. If we notice, all of these rectangles are just about the same height, which means that it looks like between 0 and this first endpoint up here, there's the same number of data values as in this next class interval right here. It varies just a little bit due to the randomness of the situation. If we look at the bins that we created, which was bins equals np.linspace 0, 1, 10, here are the endpoints of these intervals. The first interval starts at 0 and it ends at 0.111111. So this point on the x-axis over here is 0.111 repeated. Why did that happen? Why wasn't it just exactly 0.1? Well, that's because we plotted exactly 10 points starting at 0 and ending at 1.0, which is over here, which means that we only got 9 class intervals here. So putting a 10 here made us get 9 subintervals, class intervals. And so the endpoints are going to be multiples of 1/9, 0.111, 0.2222, 0.3333, and so forth until we get up to 1. Okay. So let's see how we can use that Python random function to roll a fair die. That means you have a die, which is singular of dice, and we want the numbers 1 through 6 to be equally likely to come up when we do the roll. But we're not physically going to roll a die. We're going to let the computer simulate the rolling of a die. So somehow we have to come up with a way of randomly generating the integers from 1 through 6. Those are the possible upper faces of a fair die. And we're going to use the function random to do it. So let's see what we can do. How can we make each face equally likely to come up? A fair die, by the way, using the word fair, means that we have a die where each of the faces is equally likely to come up. So let's start by assuming that in our Python program we have x equals, and then we call the random function. In that case, the x value is going to be greater than or equal to 0 and less than 1. If we multiply by 6 all the way through this inequality, then we have that 0 is less than or equal to 6x is less than 6. And now if I add 1 all the way across, we get 1 is less than or equal to 6x plus 1, which is less than 7. So that tells us that 6x plus 1 is a real number, and by using this function, 6x plus 1 is going to be uniform on the interval from 1 to 7. So now we want to get integers. If we apply the int function to this, we're going to get int of 6x plus 1 equals either 1, 2, 3, 4, 5, or 6. And these 6 integer values are equally likely. But now let's look at this for a minute, and let's look at this int function. The int function truncates the fractional part of a real number, returning an integer value. For instance, if we look at int of 2.7, the output of this function is going to be 2. We throw away the 0.7. Similarly, int of minus 2.7 is going to turn out to be minus 2. Once again, it throws away this fractional part of 0.7 to arrive at minus 2. So it's kind of interesting to notice that this doesn't look like what should happen. You might think that the int of minus 2.7 would be minus 3 by going over to the left to the next integer. But no, in Python, it just throws away the fractional part. Int of 2 is also 2. There's no fractional part to throw away. Or you could say the fractional part is 0.0 and you throw it away and you get 2. So these numbers, 2, -2, and 2, are integers. So we now know that this gives integers, and it turns out that these integer values are equally likely. And you might ask, well, why is that true? Well, if 6x plus 1 is greater than or equal to 1 but strictly less than 2, then the int of that is going to be 1. If the value of x up here is greater than or equal to 2 but strictly less than 3, then the int of that number is going to be 2, and so forth. So these are equally likely outcomes, and so this is going to be how we roll a die and get the upper face being either 1, 2, 3, 4, 5, or 6, each equally likely. Okay, so now what we would like to do is simulate the rolling of two fair dice 10,000 times and make a histogram of the values of the sum of the two dice. So here's a program that should do this. First of all, we do some importing of stuff from libraries. From the library random, we import the function random that will allow us to generate pseudo-random numbers that are more or less uniform on the interval from 0 to 1. From matplotlib, import pyplot as plt. We put this as plt here so that we don't have to write pyplot a lot in the code down here whenever we're going to use pyplot. We'll just say plt instead, a shorter reference to that library. So then import numpy as np. So these are the things that are imported. Now our program starts. The first thing we have in our program is the function die throw defined. It's going to roll one die and tell us what the upper face of the die is. So we define die throw the following way. We use this function random to generate a random number between 0 and 1 and store that in x. Then we let die equal int of 6 times x plus 1, and we saw before that that will give us a random integer, either 1, 2, 3, 4, 5, or 6, all of those being equally likely. And then when this function is called in our main program down here, we will return the value of die. Okay, so this is going to be called many times, die, die, die. Let's see what happens here. So in the main program, we set sums equal to an empty list. And we're going to start filling this list, appending to this list sums of two dice, upper faces, as we go along, 10,000 times, I guess. So let's see, bins equals np.linspace 0 to 13, and we're getting 14 values between 0 and 13. So what happens with this is we're going to have on our x-axis, let's say, a number line starting at 0, and it's going to end at 13. And we're going to have 14 points on that x-axis between 0 and 13, which means that if you have 14 points equally spaced, that will give us 13 sub-intervals. And that's what we want in this case. Okay, so now for k in range 10,000, so k will be successively 0, 1, 2, 3, all the way up to 9,999. K starts with 0. It's going to produce 10,000 values. So the last one it produces is when k equals 9,999. So then what do we do in this for loop? We're going to throw the die twice. Die face 1 equals die throw. Die face 2 equals die throw. So each of these generates a random integer between 1 and 6 and stores them in die face 1 and die face 2. Now, what we want to do then is find the sum of these two and store it in this sums list. So we can do that starting with an empty list. Sums.append, and then what are we going to append to the list? Die face 1 plus die face 2. Add those two values together and store that as an entry in this list called sums. So after we finish this loop, what are we going to do? We're going to draw a histogram and we're going to show it on our screen. The histogram function is in pyplot, but we said we'll refer to pyplot as plt. So plt.hist, and then we have that array sums, which has all the sums of the throws of two dice, the bins, which is defined up here by np linspace, this stuff, and we'll make the edge color of each vertical rectangle black so they stand out pretty well. And then the last thing is, once again from pyplot, we're going to show whatever graphics output we produced up here, and in this case it's that histogram. So that's the entire program, and we like to run it and see what happens. I'm going to run this Python program using the integrated development environment Spyder, S-P-Y-D-E-R. So here is the program on the left that we just discussed, and I want to execute that. If we look down here, this is the icon for Spyder, and it's already running. And so to execute this program, I'm going to come up here and use this little, I guess you could say, arrow pointing to the right, and it will execute the program. When we execute it, you'll notice that something happens down here. There's going to be another output. There's going to be an output window that appears here, and then we can open it to see what the output of this program looks like. So let's go up here and hit run. And what do you know? It came up automatically. Also down here we have an icon to that graphic. If the graphic didn't appear, we could come down here, click on it to see it, but it came up automatically. So here we see the distribution of values of the sum of two dice. If you look at this for a minute, you can see why we picked the bins that we did. Looking at bins equals linspace 0 to 13 with 14 points in between. 13 over here is right at this point, and that made the endpoints of each bin, each class interval, be an integer. We have one class interval going from 2 to 3, another one from 3 to 4, 4 to 5, 5 to 6, 6 to 7, and 7 to 8. Now for this class interval, using this histogram, it's really everything that came up exactly 7, because our sums list only had integers. So if we look at this, the count in this subinterval right here is, looks like it's 1600 and some. And this is the largest vertical rectangle. So the most likely outcome is that the sum of the two dice equals 7. As you approach the sum equaling 12, the probability goes down. If you start with the sum equaling 2, that's a pretty small probability given by this bar. And as you progress closer and closer to 7, the probabilities increase. So the probabilities for the sum increase until you get to 7, which has the highest probability. And then after that, the probabilities decrease. It looks kind of linear here, not like a parabola. So it might turn out that if we computationally, or maybe I should say analytically, solve this problem by hand, we could calculate the probability distribution for the sum, and we would expect it maybe to be a triangle of some sort, or at least some points that are plotted which lie along a triangular path. So what did we learn? We used how to use random in Python to do the following. We generated pseudo-random numbers, real numbers, with a uniform 0-1 distribution. It appeared that every number that was outputted by this random function was between 0 and 1, and sometimes 0 could occur, but 1 never occurs. But everything between 0 and 1 are just as equally likely to occur, hopefully, as any other. At least that's what the random number generator tries to do. Then we use that to generate pseudo-random integers, and once we saw how to do that, we simulated the rolling of two dice 10,000 times. Well, once we roll those dice, computer rolls, I guess you could say, of those dice, and we calculate the sum, what we then did was we got an idea of the probability distribution of those sums by drawing a histogram. And what we saw was when you start at 2, the probability was pretty low. It was given by a frequency histogram in our case, but you can see the probability of rolling a 2, in other words, a 1 and a 1 on the two dice, was pretty small. Then the probabilities went up until we got to a sum equal to, what was it, 7. And then after that, the probabilities decreased again until we got a small probability that the sum of the dice was 12. I hope that you enjoyed this presentation. Please stay tuned for more. Have a good day.